Same directions in this problem. We want to evaluate the surface integral over S, f dot n ds, which is called the flux integral. We've got f with components y e to the z, 3x squared y, 3y squared z. S is the surface of the solid bounded by the cylinder. X squared plus y squared equals 1. That's a circular cylinder, isn't it? And then the plane z equals -1 to z equals 2. So it's just like it's like a Coke can, right? It's just you're used to starting z at 0. We're not doing that here, are we? So the good news then is, okay, we could use, I suppose, 3 different flux integrals to represent this, right? Because if you draw this cylinder, say this is at a height, this end is at a height of z equals 2. And this end is at a height of, this guy down here is at a height of z equals 1. Then S is really not only the cylinder, the sides of the cylinder, but the end caps, the circular disc end caps as well, right? Top and bottom. So there's really 3 surfaces there. So if you wanted to calculate the flux integral directly, you'd have to set it up over the plane z equals 2, the cylinder, and the plane z equals 1, set up the flux integral for each one of those, add together. Okay, that wouldn't be any fun, right? But good news is we know that this flux integral is equal to the triple integral over E. E is the interior of this thing, of the divergence of F ds. And it works because you're given nice, well-behaved functions here. What do I mean by that? Well, the components of F are well-behaved, so the vector field F is well-behaved, and the surface S is piecewise smooth. Those 3 surfaces are all smooth. And it's closed, right? It's got to be closed for this to make any sense at all. The surface S has to be closed. Okay, so you guys tell me, what do we do first? Divergence, right? So you're using this guy as a guide, aren't you? And going from the inside out. Oh, it's telling you to compute divergence. So the divergence of F, which is del dot F. All right, you guys tell me, derivative of this guy with respect to x is 0. Derivative of this guy with respect to y is 3x squared, right? Derivative of this guy with respect to z is 3y squared. Everybody agree with that? Okay, so cool. We've got our integrand. Now, and in order to evaluate our integral, well, okay, hold on. Let me set it up before I say that. Let me set it up. So our flux integral is going to be equal to the triple integral of 3 times x squared plus 3 times y squared. What do you think I'm going to do with that 3? Pull it out, right? So x squared plus y squared dv. Now, we have to figure out what our differentials are, but first let's figure out our region of integration. Well, what do I mean when I say region of integration? I'm talking about the outer 2 integrals. I know what z goes from. So if you wanted to go dz, right, you can be pretty confident, and then figure out your differentials out here. Well, maybe we should hold off on that. So what does z go from? It wasn't 1. I had 1, but of course it was supposed to be -1, right? -1. Okay. So -1 to 2, right? Okay. Now, really, if you project this surface down into the xy plane, would be the plane of integration for the outer 2 integrals, right? What are you going to get? Well, aren't you going to get a disk with boundary curve x squared plus y squared equals 1? The generating curve of the cylinder. So the disk is, or the actual region R is actually x squared plus y squared less than or equal to 1, right? It's the interior of that curve as well. Now, am I going to bother setting that up? Yeah, I will, because it's good review for the final, but normally no. Okay, so the disk radius 1, something. I'll do this myself, and if it's a bad-looking circle, too bad. Well, okay, I've drawn worse. So that's, okay, the interior then, right, would be, that would be the disk x squared plus y squared is less than or equal to 1. Okay, if you went with, say, the usual order, this is, again, I would skip this step if you're just going for an answer here. dz, dy, dx. If you go with the usual order of integration, that corresponds with vertical rectangles, right? So what formula is going to give you the top of that rectangle? We need that for one of our limits of integration, the middle top limit of integration. So y equals the square root of 1 minus x squared. You solve the equality, the equation of the circle for y, right? And then what's the, okay, what do you get for the bottom of that rectangle when you do that? Negative square root of 1 minus x squared, right? So your inner limits of integration go from negative 1 minus square root of, the opposite of the square root of 1 minus x squared. Okay, that's what I was just trying to spit out. To the square root of 1 minus x squared. And then what does x run from? Negative 1 to 1, because the radius of that circle is 1, right? So negative 1 to 1. So is that something you should be able to set up? Yes. Would you ever evaluate this integral as is? No. What would you do? You would switch to, I suppose it'd be called cylindrical here, right? But it's really the 3D version of polar coordinates. So then this becomes 3 times, okay. What does the integrand become in polar coordinates? R squared. We have an extra factor of r, and then dz stays as is, dr d theta, right? Okay, so z stays as is in cylindrical coordinates, doesn't it? So inner limits, they stay what they were. The r runs from, okay, think of a representative spoke, right? What do the limits on r then range from the part of the spoke closest to the origin to this part on the circle, which would be 0 to 1. And then, of course, you have to trace out that entire region, that entire circular region from 0 to 2 pi, don't you? There you go. Would that be very hard to evaluate? No. In fact, this is such good review. I'll go ahead and evaluate this guy, because what am I going to do here? Since, okay, this is r cubed, right? So how can you rewrite this to just organize it better? Can't you rewrite it as 3 separate integrals, single integrals multiplied together, when the limits of integration are constant, and you can, with the integrand, separate the function of r from the function of theta from the function of z? Well, there's only a function of r, so yeah, we can do that. So if we do the one with theta, it's just 3 times the integral from 0 to 2 pi d theta, isn't it? 1 d theta. And then do the one with r, integral 0 to 1 of r cubed dr, and then integral negative 1 to 2 dz. Doesn't that look easier on the eyes? I think it does anyway. And I can calculate the integral from 0 to 2 pi really easily if the integrand is 1. What is that going to be? So, well, 2 pi for that, right? 2 pi. And then, okay, what's the integral of r cubed with respect to r? 1/4 r to the fourth, but you're evaluating that r to the fourth from 0 to 1, aren't you? So just 1/4 there times 1. Okay, then what about this guy? That's z. If you integrate it, it's z evaluated from, so it's a product here, -1 to 2, which means you just plug in those, apply the fundamental theorem, and you get 2 minus -1, 3. Yeah. So we get 6 pi over 4 times 3. Okay, but what is that? So that's 3 pi over 2 times 3, or 9 pi over 2. There you go.